So what do we have going on here in this problem? We've got a function, right? What's a function representing?
Rate of potato consumption.
A rate of potato consumption. I'm going to circle this word rate. That's the important piece of this. This function that we're given represents a rate, okay, in millions of bushels per year. So an amount of something per time period. Okay? We want to know how many bushels were consumed during a certain time period. So we need to go from a rate function to an actual numeric value, right? A numeric value of the amount, not a rate, right? So we need to convert from rate to amount. And so what I'm going to do for us to sort of start thinking about this is I'm going to sketch a little graph here of our function, which this is not what our function looks like, but there's some function, okay? This is a function that is being graphed on a time and a consumption axis, right? Time consumption axis. Do y'all agree with that? C of t, right? C of t is the y value, t is the x value on in our coordinate plane, right? True?
Mm-hmm.
Okay, wonderful. In fact, we could just call it C. I don't have to necessarily call it C of t. Either way, it doesn't matter. Now, what are the units of C? This is millions of bushels per year, right? And what are the units of time in this particular case?
Years. Since the beginning of 70, I guess, but like 1 year each.
Yeah, each mark we put will be a year. Okay, so how do we get from those two things, how do we get millions of bushels, the numeric amount that we want to get?
You plug in a number for t.
Well, if I plug in a number for t, that's going to give me millions of bushels per year. I just want millions of bushels. How many millions of bushels? So let's think about.
Get rid of the year. So you have to get rid of the year. Multiply it, I think.
Right. If I were to take C and multiply it by T, that would give me millions of bushels per year times year, right? And what would happen with my years? My years would cancel out. True? And that would just give me millions of bushels. That's what I'm looking for. True?
Yes.
Okay, great. So how do I do that with a graph? How do I multiply this thing by this thing, given some function in there that represents the amount of C?
You could find the average rate and then multiply that by the time.
All right, we could find an average rate and multiply it by the time. Okay. How would we find the average rate of that then?
You integrate.
Okay, and part of it is an integration, right? And what does an integration do, right? An integration is just finding us a bunch of little rectangles underneath this curve, isn't it? Giving us a bunch of little areas.
Yes.
Right. That's exactly what this integration does. Let's say this is how far we want to go, let's say. And what are the areas of each of these rectangles? Each of the areas of these rectangles are a t times a c. And when we get an infinite number of those c's times t's, we get an exact value for the area underneath this curve. Does that make sense? So we don't even need to find the average value. We could find the average value, but we don't need to, because we can find the exact value of the area underneath this curve by just simply doing an integral of our function. And the integral of the function effectively is multiplying these width units, these t's, these years, by these y values, or these c values, these millions of bushels per year, to cancel out the years with the divided by years to just make it millions of bushels per year. Does that make sense or no?
I think it will make more sense to me as we move on. So yes.
Okay. So I mean, the idea here is, right, that anytime we have a rate function, this function is in terms of some number of things per time period across a time period. And so if we integrate this rate function every time, it should give us an actual numeric amount of the thing that we're looking for. That's the whole idea here, is that the integral of a rate function is the amount of that thing. And so here we just want to integrate our rate function from, well, the beginning of 72 to the end of 73. So if t is the years since the beginning of 70, what would beginning of 72 be? Beginning of 70 would be year 0, right? Beginning of 72 would be year 2. And end of 73 would be 4, right? End of 73 is the same as the beginning of 74, so 2 to 4. And so what this is doing is it's just multiplying the years from year 2 to year 4 by this function with an infinite number of little points in between. And so all we have to do is integrate the rate function from 2 to 4, and you'll use your calculator to do that. Did I show you guys how to use your calculator to integrate things last quarter or no?
No.
So
No. Oh, okay. Well, then I need to show you how to do that. All right. It's really easy. You're going to hit math, and then you're going to hit option 9, which says FNINT with a parenthesis, perhaps, or it may just look like an integral sign. If it just looks like an integral sign, then just put in your 2, put in your 4, put in your function, put in your dx. And whenever we type it into our calculator, we'll just do it in terms of x. So you'll write 2.2 plus 1.1 to the x dx. Does anybody's not come up with an integral sign though when they hit option 9? Anybody just show up like this, FNINT parenthesis?
Yeah.
Yeah, yeah. So if that's the case, you're going to type in your function, which was what, 2.2 plus 1.1 to the, we'll use x. So type in the function, then a comma, then an x, then a comma, then your lower limit, then a comma, and the upper limit, and then close your parenthesis. And that ought to give you the same value. And what do we get? Somebody must have a value for that already.
7.066.
7.066 millions of bushels of potatoes. Perfect. Sounds good. Any questions on that? Anybody not get that value? Everyone's good there?
Wait, so you type in the function and then you type in the x and then comma x, but what's the, and then 2, 4.
Yeah,
Okay.
2 is your lower limit, 4 is your upper limit.
Yeah. All right. Cool.
Wait, and then if you divide this by the time, then couldn't you figure out the average rate using your calculator?
If you divide it by, yeah, you can find the average. Yeah. Well, if you divide your answer by by, what did you want to divide by? By like 4 minus 2?
Yeah.
Yeah, that'll tell you the average rate, yeah. And so like you were saying, was it you that was saying find the average and then multiply by the number of the years?
Yeah.
Right, and so that's exactly what this would do. Finding the average would be dividing it by 2, and then you'd multiply it by the number of years, which was 2 years, and it just effectively comes out to be this integral that we did to begin with. But yeah, you're exactly right. Any other questions on that? Everybody good? All right, I'll give you a second here to read this one, and then we'll talk about it. Any thoughts on this? This should be similar, right?
I have no idea if this is anywhere close to right, but my first instinct would be to use like trapezoidal approximation on it.
Okay, that's a good plan. So we're looking for, we're given a rate, right? And if we want to find the actual number of gallons pumped from the rate in gallons per minute, we want to do an integral from 0 to 60 of that rate function, right? But since we're not actually given a function, we're going to have to approximate this integral using some method. And so, yeah, the trapezoidal method seems like a great way to go. Let's approximate it using the trapezoidal rule. Good for us to practice these rules again. So, how do we do the trapezoidal rule? Trapezoidal rule says h over 2, where h is b minus a over the number of subintervals. So how many subintervals do I have between 0 and 60 if I break it down every 5 minutes?
12.
Yep. So b minus a over n over 2. And then first y value, 2 times the second y value, 2 times the third y value, 2 times the second to last, and then just times the last. Good or no?
Good.
And you've got a calculator, so I will let you evaluate out what that is and let me know what it is when you get it.
I got 3,740.
That's different than what they got last period.
Oh, okay.
I got 4,299.
That's also different from what they got last period.
I got 8,598.
That's also different from what they got last period.
3,582 and a half.
That's what they got last period. And lots of people got that. So you probably just typed it in wrong if you didn't get that. 3,582.5 sounds like that should be pretty accurate anyway. We should be able to have a reasonable guess. What is this, gallons, right? Because we know that we're around 60 each time, right? Close to 60. And we had 60 minutes in the hour. So 60 minutes times 60 gallons about per minute would be about 3,600. So that seems fairly reasonable. Yeah, I don't know what happened to some of you there. You might have plugged in something wrong. Must have plugged in something wrong. Everybody feel like okay about that or no?
I feel okay about it.
All right. No questions. Let's look at another one. I'll give you guys a minute to look at it and read it, and then we will talk about it. All right, we have an idea what we want to do here. We're looking for how many people are in this amusement park, right? At 6 p.m. So the number that are there at 6 p.m. should be we're talking about starting at noon, right? We're talking noon to 6. From the number at noon, we should add the number that enter and subtract the number that leave, right? That's kind of the basic idea of this, to figure out how many people are there at 6, figure out how many there are when we start, how many people come in, and how many people leave.
Yes.
Yeah, hopefully that seems reasonable. Okay, so how many were there at noon? That should be the first part. That's easy.
3,000.
3,000. Okay. And how many people enter the park? Well, all we're given is a graph of E of t. E of t is a rate. So we're going to need an integral of E of t from when to when? From t equals
0 to 6.
0 to 6. And we're going to need to subtract, let's see, L of t is also a rate. So an integral from 0 to 6 of L of t dt. Okay. And so That 3,000, like we said, is still just 3,000. But how are we going to find the integral from 0 to 6 of e of t dt?
Just use the graph and like break it down into shapes.
Yeah, break it down into shapes and find the area underneath it, right? That's what the integral is. It's just an area. So that little rectangle in the middle is the easiest one, right? That's 600 by 1, so 600 there. What about this first trapezoid here? It's got a height of, sorry, a base of 400, another base of 600. So 1,000 over 2 times 3 should be, what, 1,500? And then this one, 600 and 500 over 2 times 2. Height of 2 divided by 2. So what's our integral from 0 to 6 of e of t dt? Should be 3,200, right?
Yeah.
And let's see, L of t is just this function. We're given the function. All we need to do is integrate it using our calculator from 0 to 6. So what do we get when we integrate that function from 0 to 6? Anybody?
2,106.411.
All right, and so if we add those and subtract that, we'll say that if a person hasn't fully left the park, we'll just say that person hasn't left because we're talking people here. We're not going to have fractional people. So what does that come out to be? Looks like what, 6,200 minus 2,106. What should that be? 4,094. Did I do my arithmetic correctly?
Yeah.
Oh, good. All right. Anybody have questions on that? Does that make sense? We're all good there? Not good? Good. All right. In that case, I'll assume that means everybody's good since you all just ignored my questions. We'll move on to the next thing we're going to talk about, which is the beginnings of what I was talking about earlier, differential equations. One other thing I want to note about the rate and the accumulation problems. Those are really popular on the AP test. They really show up a lot, but we got to be careful. Don't just assume a function that's given to you as a rate function unless it says that it is. Oftentimes, they will give you like two different equations like we had there with the E of t and the L of t, and one will be rate and one will not be rate. It'll be an actual amount equation. So be careful to distinguish between those. So as we start to do our free response questions in a few weeks here, we're going to really be looking at these accumulation type problems a lot more. All right, so we're going to find some differential equations here. That's what we're going to work with, is differential equations. And a differential equation is just an equation that involves a derivative, hence why they call it a differential equation. So when we solve a regular equation, like suppose I give you x squared equals 9 to solve. Right? What do you do to solve that? You square root it, right? And you get x equals,
3.
or you get x equals
-3.
negative 3, right? You get 3 or you get negative 3. Right? Some equations have one solution, some have no solution, some have 2, 3, 4, 700, any number of different solutions to some regular old equation. But the idea of solving an equation like x squared equals 9 is always you are looking for every x value that satisfies that equation, which is why we get 3 and we get negative 3, right? They both satisfy x squared equals 9. Negative 3 squared is 9 and 3 squared is 9. Well, it's the same idea with the differential equation. One of these is an equation that has a derivative in it. Okay? Except that the idea is instead of looking for a numeric value that satisfies the equation, you are looking for all of the functions that satisfy having this as its derivative. So dy dx equals this. It's a differential equation of what we call the first order because it's a first derivative. And to solve it, we just need to find all functions that have this as its derivative. I could have a second order differential equation. There's a second order differential equation. So is this. Second order differential equation. Complicated one we won't have to deal with in here. But it's a second order differential equation because the highest derivative involved in it is a second derivative. Everybody get that? Okay, so how do we then find all of the functions that have this as the derivative?
You take an integral?
We take an integral. In order to integrate secant squared x plus 2x plus 5, it's got to have a dx attached to the end of it, though. Well, good news is I got one in the denominator here. We'll just bring it over here. Multiply both sides by dx. We have dy equals secant squared x plus 2x plus 5 dx. And now what we do technically is we integrate both sides of this. And on the left-hand side, we get y, right? And on the right-hand side, we get tangent x plus x squared plus 5x. Good or no?
Do you need a plus c or no?
Okay, so yes, we do. And that's why I've said good or no. And also why I've left this giant gap over here, right? Because when I integrate something, I always get a constant, don't I?
Yes.
Right? I integrated two different things, I get two different constants. Well, we can simplify things a little bit because I know that I'm integrating both sides and getting two different constants. I don't really need to put a constant on both sides, right? Because if I have y plus constant 1 equals this plus constant 2, I could just subtract constant 1 over here. And then I've got y equals this thing plus constant 2 minus constant 1, right? And what's constant 2 minus constant 1? It's just some other constant, isn't it? So effectively, we just need to put a constant on one side. Traditionally, we will put it on the side with the x's, with your independent variables. Good or no?
Good.
Very easy and no different than just finding an integral, right? This is, since we have a plus c attached to the end of this, this is what we call the general solution to this differential equation. And I could go in here into Desmos. And what was my function? Tangent x plus what? Plus x squared plus 5x. Is that right? Zoom out a little bit, right? Is that what it was? plus a constant?
Yeah.
Right. I could have this. This is a solution to it. So is this shifted up a little bit. So is this shifted up even more. So is this. Right? So is this. So is this. They're all solutions to it. They look different, but they're all solutions to that differential equation, because when I take the derivative of each and every one of those, I get right back to this original thing that I had, dy dx equals secant squared x plus 2x plus 5. And that constant doesn't affect it. Now, what if, let's go back here to Desmos. What if I said that I needed it not to go through the point 0, negative 6 pi, but I needed it to go through the point 0, 0. Right? Then my constant would have to be a certain fixed value, wouldn't it? Because some constants don't let me go through the point 0, 0. In fact, for this particular function, whatever my constant happens to be here, I had a 5x plus 9, right? Whatever this constant that I happen to have here happens to be my y-intercept, right? I put a 3 there, my y-intercept is 3. If I put a negative 3 there, my y-intercept is negative 3. If I put a minus 3 pi, my y-intercept is minus 3 pi, right? So we could have some extra restrictions on our differential equations, saying that our function needs to go through a certain point. Okay? And so that would restrict the constant to only one specific value. That makes sense?
Yes.
Okay. And it wouldn't have to be, it doesn't have to be a y-intercept. It could be any value. I could say I want it to go through the point 1, 1, or I want it to go through the point, 17 pi, comma 38. Okay. It doesn't matter what that value is, what that point is, it still restricts it to be one specific function. And that's what we're going to mostly be dealing with. So this is just called a differential equation, and this is the general solution to it, because there's no condition, and we call it an initial condition. There's no initial condition given to us that we need to solve and find a specific constant. And we get a general solution. When we solve for a more specific solution where we find that constant, that's what we call a particular solution. And we call those often initial value problems. And that's what we're going to do with the majority of these. And that's what we're going to do for the rest of the time that we're doing lecture here for today. So we're going to take a differential equation like this one, dy dx equals e to the x minus 6x squared. And we're going to say, we need the solution to this differential equation to pass through the point 1, 0. Okay? We're going to find the particular solution, that one unique solution that has this as its derivative that goes through this point. Does that make sense what we're doing? Hopefully that's very clear. If not, please tell me how unclear it is and I will try to help you.
It is clear.
Oh, wonderful. Okay. So in order to do that, we still need to take an integral. So we're going to still bring that dx over here. And integrate both sides. And like we said with the first one, having two constants doesn't really matter because I can always subtract one to the other side. So we'll just leave the dy when we integrate it as a y. And on this side, we'll integrate and put our constant. So what's the integral of e to the x?
E to the x.
E to the x. And the integral of minus 6x squared?
2x to the third.
Minus 2x to the third. And we have to add some constant. And now that we have an initial condition, we should be able to plug in 1 for x and 0 for y to find that constant. And what do we end up with? Our constant is
2 minus
2 minus e. And so our final solution here ought to be y equals e to the x minus 2x cubed plus 2 minus e. And if we were to go in and look in Desmos, we have e to the x, I have minus 2x to the third, right, plus 2 minus e. So there's the function. It goes through the point 1, 0, which it was required to do. And if I take the derivative of that function, derivative of e to the x is e to the x, derivative of minus 2x cubed is minus 6x squared, derivative of plus 2 is 0 because it's a constant, and derivative of minus e is 0 because it's a constant. So it satisfies all of these conditions. It solves the differential equation, and it works with our initial condition. Good or no?
Makes sense.
Great. Let's do another one. You guys want to try and do this one on your own?
Sure.
Great. All right. I will give you 2 or 3 minutes to look at it and see if you can figure it out, and then we'll talk about it together. Ready, go. Do this. So we'll bring the dx over, and we'll integrate. So that just gives us y. What's the integral of sine x?
Negative cosine x.
And the integral of 2x?
X
X
squared.
squared.
Okay. Plus a constant. Our initial condition is 0, 3, because that's a y-intercept, right?
Yes.
Yeah.
So we'll plug in 0 for x and 3 for y. And cosine of 0 is 1, so that's negative 1. Bring that over, that's constant is 4. And so we end up with y equals negative cosine x plus x squared plus 4. Good or no?
Good.
Good.
Great. That's it. That's all there is to do with that one. Any issues there? Let's do another one. Let's do this one together. So we're going to do the same thing, right? Bring our dx over and integrate both sides. And we'll get y equals what?
X squared over 2.
Minus
Tangent x.
Tangent of x.
plus,
C.
right? And when y is 3, x is 0. So 0 squared over 2 is 0. Tangent of 0 is 0. So our constant is just 3. And this seems nice and straightforward. Y equals x squared over 2 minus tangent x plus 3. Everybody feel good about that?
Yes.
Well, you shouldn't. Okay. And there's a reason why. What's different about this function from the last two that we looked at? The cosine x plus x squared plus 4 and the e to the x minus 2x cubed plus 2 minus e, the last two initial condition ones. What is different about this function? What makes this function, what makes it different?
Discontinuity.
Yeah, it's got discontinuity, right? There's an asymptote because of the tangent x. In fact, there are an infinite number of asymptotes, right? There's asymptotes at x equals, we'll say discontinuities, but they are asymptotes, right? At x equals positive or negative, what, pi over 2 and 3 pi over 2 5, pi over 2, and so on, right? Forever? True? Y'all agree with that?
Yeah.
So when we have discontinuities in these solutions to our differential equations, we've got to take those into account. And so what I will say about that is that we need to only, or we'll say it's valid only on the continuous portion. Oh, I've lost my ability to write. On the continuous portion of the domain that includes the initial condition. Wow, I don't know what's up with my pen right now, but it's having some issues. Sorry about that. Hopefully you can read that. It's valid only on the continuous portion of your domain that includes your initial condition. So our initial condition says that x is equal to 0, right? So between which two asymptotes does x equals 0 fall?
Positive pi over 2 and negative pi over 2.
Right. So we will say that this is only valid for negative pi over 2 to pi over 2. Because outside of that interval, it doesn't matter what the constant is. We could have a constant of 1,000 between pi over 2 and 3 pi over 2. And we could have a constant of, negative 5 from negative infinity all the way to negative pi over 2. And that doesn't affect the fact that the derivative is still equal to this, x minus secant squared x, and it doesn't affect the initial condition. The only portion that affects the initial condition is this little piece. Does that make sense? For now.
Wait, could you explain that again?
Right, so we could have any constant. We don't have to have a constant of 3. We could have any constant outside of negative pi over 2 to pi over 2. So for example, from negative infinity to negative pi over 2, I could have a constant of plus 1,000. The derivative is still equal to this. And as long as on the interval between negative pi over 2 and pi over 2, the constant is 3, it still satisfies my initial condition. Right. Same with from pi over 2 to infinity. I could have any constant I want. I could say from pi over 2 to infinity, it's got a constant of plus 1,000 pi. That's fine, because it doesn't affect the fact that it still has a y-intercept of 3, as long as between negative pi over 2 and pi over 2, I choose to have a constant of 3. Does that make sense or no?
Yeah.
Okay. Yeah, so you always got to choose only the continuous portion of it that includes the initial condition. Say that's where it's valid. That's it's an important little point to these differential equations. And for the last ones, we didn't have to worry about it because there was no discontinuities, right? No discontinuity, no discontinuity. Didn't have to worry about it. This one had discontinuity, but we weren't looking for a specific solution. So we don't have to worry about the discontinuities on that one either. We got any value C. But here, between negative pi over 2 and pi over 2, it's got to be plus 3. Any other pieces of the domain, put any constant you want. But this is the solution that we will write down. All right, this one right here is the last one we're going to do today. And I will give you guys, I don't know, a minute or two to work through it on your own. And then we'll talk about it. Sound good?
Yep.
Oh, good. Ready to go. So you brought the dt over. You integrated both sides. You got a equals, and hopefully you remember the integral of 1 over t to be natural log absolute value t. And then the integral of negative 1 over t squared, what did you get for that? Plus
T to the negative 1.
t to the negative 1, or I'm just going to write it as 1 over t, same thing, right? Plus 6t plus your constant. When a is 0, t is 1, so natural log 1 plus 1 plus 6 plus your constant. What does that give you for your constant?
Negative 7.
Negative 7. Good. Okay. So our final equation is a equals the natural log of the absolute value of t plus 1 over t plus 6t minus 7. And this has some discontinuity, right? What is there's only one place where it has a discontinuity, but we know that t cannot be what?
0.
0, right? The absolute value allows us to have negative values of t. If this wasn't inside of an absolute value, we would only have values of t that were greater than 0. But so the domain of our function is negative infinity to 0 and 0 to infinity, but we don't put both of them. We only put one of them. We only put the one that includes our initial condition of t equals 1. So which one will that be?
0 to infinity.
0 to infinity. Perfect. And I don't know. I've been teaching this class for 5 or 6 years at least now, maybe more than that. I don't know. And even last quarter, I don't know. I've said it a bunch of times in class that you only include one piece of the domain. You only include the singular piece of the domain that includes that initial condition. But for some reason, people love to just put the full domain of the function. Okay? So when you write out that interval, there should be only one interval every time, no matter what, for your differential equation solutions. Okay? Anybody have any questions on what we did today?